Hi. More AI stuff. We're presenting SnAIp, our machine learning and snap approach. I think I can kind of skip this slide because we all know that machine learning is everywhere in translation and natural language processing and so on, and we just saw some examples for this, some really cool examples. But yes, machine learning is getting a big thing, which means that it's getting a big thing in CS education as well. So there are a lot of cool tools, just as we saw in Craft to Learn, and there's machine learning for kids and Cognimates and Alpaca ML and stuff like this, which is really cool. But we made two observations. So first of all of these approaches focus on supervised learning, text recognition, image recognition, stuff like this, and classification, and they are not focusing on breaking the black box law. So as we just saw, you use TensorFlow and can do really awesome stuff with it, but we want to look into the black box. How is the actual learning happening? How does a computer learn? And that's why we designed we formulated some design principles for an approach where we first of all want to look behind the scenes. So we want to see how the magic happens. We want to see into the black box, how does a computer learn? Furthermore, we want to have everything inside the tool. So no external API calls, no JavaScript, no nothing, everything in SnAIp. Everything just blocks. And as you can see, this is the thing we will look into in a few minutes. And every custom block is just made of other blocks. Then we wanted to have useful projects, overlearning projects. So cool stuff like, I want to have an agent who plays Pong and always wins, or breakout, or who finds pattern in my data if I want to use SnAIp to analyze data. And last but not least, we want to have the models as real artifacts. And that's why SnAIp is so great, because we can import and export CSV. And we have these tables, which we will look into now. How does it work? So SnAIp, we first of all started with one could say, three major machine learning paradigms. So we started with reinforcement learning, which is pretty close to human learning. We made these graphics with sweet robots and everything. And essentially that is how reinforcement learning works. So we have to, the agent has to assess the current state, for example, in a game, which is my current state. According to the current state, he has to select and execute an action, and then get rewarded or punished. And according to the reward, he has to update his model for choosing which action in which state. And yeah, let's see how we did this in SnAIp. First of all, with this example, you might know it from being one of the featured projects currently. Maybe I'll zoom it in. So let's first of all have a look at the monkey trying to catch a banana. Up there's the success rate, which we apparently didn't translate. Just let's watch for a minute. So by now, the monkey apparently has learned when to jump if he's not jumping beforehand. jumps over the barrel successfully. Well, how is this implemented? If you remember the 4 steps of this learning loop in reinforcement learning, first of all, we set up a model where we save all our data, and then it's just that. It's just 4 steps. First of all, we determine the current state. In this particular case, we just use the x position of the barrel and divide it by 10 just to reduce the states. Then we look up in our model what would be the best action in this current state. We execute this action, in our case jump or do nothing, and then we get a reward. If we hit the barrel, we get punished by 10, and if we didn't hit the barrel, we get rewarded with 1. And then we update our model. Okay, what is now is the cool thing that we can have a look in our model and see what's happening here. So in the first column, we have the states in the sense of the distance to the barrel. In the next column, the B column, we have the current reward for jump in this particular state, and then we have the reward for do nothing. And as you can see, those values updates. So we are kind of with a not that good success rate currently, actually. But this way we can actually see why does the monkey jump, why does it not jump, and how are these values changing. It's just our reward, and in this implementation we have some factors like discount factor, learning rate, and stuff you would do if you do reinforcement. So let's have a look at another example, which is this Pong game, and run it in Turbo. The left panel is just a perfect AI, always being at the level of the ball, while the right one is learning to play. And as you can see, it took about 20 seconds in turbo mode for the agent to learn it might be a good idea to stay on the same level as the ball does. And the interesting thing is, if you look at the implementation of this Pong game, it's essentially the same. So there's only 3 things you have to change. Well, maybe 4. You have to specify the available actions for the agent. Now it's moved down to nothing. Then we have a different state. So this time it's the Y position of the paddle minus the Y position of the ball. Then we'll get our best move, run it, and we have to specify a reward, which is now different to before. And that's everything that's changed. And we can use the same stuff on Pong or Breakout or whatever you want to do, your own games. What we have, I think that's still open. If you remember this table, this is the actual data structure because we use an algorithm called Q-table learning. So no neural nets, nothing, just this table. And if you do this in the classroom, we start with an unpacked activity where you get rewarded in the best possible way, eating chocolate chips. There you have like the same principle of having a table with chocolate chips, and according to the table, you choose an action and then execute. In the next step, we have this banana hunt in a puzzle activity. So we use the visualization with the robot you saw, and it's the student's task to put the puzzle pieces in the right order. And beforehand we discussed the principles and the similarities to human learning. And then they have to pin their own game. So if they implemented like their own Pong game beforehand, or if the teacher gives them a template, it's now their task to pin their own game and make it intelligent. We have a teaser alert, because we are about to finish our part B regarding unsupervised learning. We once more have sweet robots. And yeah, we fulfill the same design principles and have once more an unplugged activity where you have to find as much gold as possible in the Old West, and then implement it in SnAIp itself without any additional JavaScript, just anything. So in summary, we provide a framework, call it a library, for machine learning within SnAIp, as well as a curriculum and some ideas what you can do in the classroom. And therefore, break open the black box, you can see the learning, you can discuss the learning, and you can even with like older students discuss the Q learning algorithm itself. It's implemented in SnAIp, you can have a look at it, you can experiment with it. We emphasize a constructionist perspective and look beyond the dominating classification and image recognition examples. We have all the materials here. We had our workshop on Monday. Here. We have, for example, some of these, give me just some of those. Some cards for the students, which help them in pimping their own game, which help for each of the steps, creating the model, detecting the state, and stuff like this. If you were in the workshop and want to know more, just talk to us. We have all the stuff here, as well as on SnAIp.org. Although most of them, for now, just in German, but we are in the process of translating them. Thank you.